Hello everyone. In this video we're going to be going through LeetCode problem 146, LRU Cache. So this problem has a 99.3% popularity. Is the second most popular question after two-sum. This says to design a data structure that follows the constraints of least recently used cache. Now what is least recently used cache actually? Well, cache is basically the amount of memory that's stored for easy retrieval. So think of your computer. Let's say you go to a website and access Amazon.com, and you do that every day. So that will be stored in your cache. But then once in a while you might go to a different website. It might take a second or two to load it because that one is not stored in your cache. But after you access it, it will be stored. But the cache has a limited amount of space. So that's why this problem is so important, because you want to remove the stuff that you haven't used in a long time. And so to do that, we're going to implement this solution. So LRU Cache will pass in an int capacity. And we'll do that with a positive size capacity. Then we'll have a get method that passes in an integer, the key, and returns the value of key if it exists. Otherwise, we'll return the default value of -1. Next, we're going to have a put method, which will input the key and the value. And if the key already exists, it will update the key and the value. Otherwise, add the key value pair. And if the number of keys exceeds the capacity, this is where the least recently used cache method comes in. It will evict the least recently used key. And the functions get and put must each return O of 1 average time complexity. So let's look at the example they give us. And instead of looking at the input and output, we'll just go through the explanation. So the first thing we're going to do is instantiate LRU Cache class to a new LRU Cache and pass in a capacity of 2. Then we're going to put the key value pair of 1, 1 into the cache. And then we're going to put the key value pair of 2, 2 into the cache. So as you can see here, the cache equals 1, 1 and 2, 2. Next, we're going to get the value of 1. So we're going to pass in the key, which will return the value 1. Now we're going to put in key 3, value 3. So this is where you have to activate the least recently used solution. So the last key, the least used key was 2. So we're going to evict key 2. So the cache will become 1, 1 and 3, 3. And the reason that 2, even though we put 2 in after 1, we accessed 1. And so 2 becomes the least recently used. So then we're going to try and get the 2, and it's going to return the default value of -1 because it's not in the cache anymore. Now we're going to put 4, 4. So the least recently used key is 1 because we put 3, 3 after we access the 1. So 3, 3 is now technically more used than the 1. So it's going to evict the 1. So the cache is now 4, 4 and 3, 3. Then when we try and get the 1, it's going to return -1. It's not found. Get key 3 returns value 3, and get key 4 returns value 4. All right, let's see how to implement this. So let's take care of some overhead information first. What we really need for this problem is a hash map, which has the key value pair. But a hash map doesn't consider ordering. And so we need a linked list to keep everything in order. And that's where a LinkedHashMap comes into play. It extends the hashMap class and implements the map class, which in turn extends the sorted map. So we get the sorting as well. This allows for key value pairing and also maintains the order. So this is the syntax here. LinkedHashMap, we're going to pass in the capacity. We're going to have a float for the load factor, which I'll explain in a minute, and a Boolean for the type of access that we want to use. So capacity is the number of buckets in the LinkedHashMap. In the LeetCode example, we passed in a 2, so the capacity was 2. The initial capacity is simply the capacity at the time the LinkedHashMap is created. So if we had a capacity of 1,000, you wouldn't automatically assign the capacity limit to 1,000. The initial capacity might be like 100 or something. So load factor is the measure of how full the linked hash map is allowed to get before its capacity is automatically increased. So let's go back to the capacity of 1,000. Let's say the initial capacity is 100, and you put 75 entries in, and then the load factor kicks in and says, oh, well, we've got 75, that's the load factor, so now we're going to increase the capacity to 200. And this will keep working all the way up until we hit the max capacity of 1,000. So as a general rule, the default load factor, 0.75, offers a good trade-off between time and space. So when the number of entries in the hash map exceeds the product of the load factor and the current capacity, then the hash map is actually just rehashed. And finally, the access order determines how the data in the hash map is retrieved. So if access order is true, it takes into account when the data was last accessed, which is just perfect for this problem. I actually think LinkedHashMap was created just for the LRU cache situation. So if access order is set to false, it takes into account when the data was last inserted, like a stack or a queue, which we don't care about in this case. So the LRU class will extend the LinkedHashMap. Now the LinkedHashMap class will be accessed using the super keyword. We're going to use LinkedHashMap's method getOrDefault, which will pass in a key and return the value. Otherwise, it will return -1 if it doesn't find it. We're also going to use the put method, which will do put in the key and the value. Now the put method behind the scenes calls this remove eldest entry function, passes in the key and the value. So this is a linked list method, returns Boolean true or false. And the way we're going to determine true or false is we're going to use the size method and return the number, which returns the number of key value mappings. So we're going to compare size to the capacity. And if size is greater than capacity, then we're good to go. But if size becomes greater than the capacity, then we have to remove the eldest entry. Okay, so let's code this. So public class LRU cache, this is what LeetCode gives us. We're going to extend the linked hash map class, passing in an integer for the key and an integer for the value. So the first thing we need to do is define an integer capacity to store the capacity that gets passed in, because we need to use that later in the remove eldest entry method. So public LRU cache int capacity. So this is the constructor for LRU cache, which is going to call the constructor for the linked hash map class. So it's going to pass in the capacity. It's going to pass in that 0.75 that we talked about and pass in true for the access order. Then we're going to assign the local variable capacity equal to the passed in capacity in the constructor. And that is pretty much it for the initial solution. Now we need to implement the get method. So we're going to pass in a key, and we're going to return LinkedHashMap's method getOrDefault, which will pass in the key and return either the value or -1 if it can't find it. Then we need the put method, which will pass in the key and the value. And this is just basically going to call LinkedHashMap's method put, passing in the key and the value. Now, this put method will call this remove eldest entry. And its input parameter is map entry key value, and they'll call it eldest. And all this is going to do is return if the size is greater than the capacity. And again, that gets called automatically through the put method. And that is pretty much it. So let's run this through the debugger, see if that doesn't help. So I use the first example, or the only example they gave us. So let's step through this. So the first thing we're going to do is instantiate a new LRU cache, passing in the capacity of 2. So this calls the constructor, which calls the LinkedHashMaps constructor, passing in 2.75 and true. And then we assign this capacity equal to capacity, which is 2. All right, so we're good to go. So the first thing we need to do is put 1, 1. So key 1, value 1 into the cache. So we use the put method, 1, 1, and you see automatically it called this remove eldest entry. And the eldest entry is 1 because it is the only key value pair we have in the cache. Size is good to go, so we add it to the cache. So if you look at cache, it's now size 1, 1, key 1, value 1. So now we're going to put the 2 in. Again, we're going to call this remove eldest entry. The eldest entry is still the 1, and size is good to go. So puts 2, 2. So now if you look at the cache, 1, 1 and 2, 2. Key value pair of 2, 2. Okay, so now we want to get the 1. And this calls the get method, passing in the key. And because we have 1 in the cache, it's going to return the value 1. Now we're going to put 3, 3. This is where the fun happens. So key 3, so we're going to look at the eldest. Now, because we put 1, 1 in before 2, but we accessed L1, or accessed 1, after the 2, the eldest now becomes 2. And so the capacity, or the size is actually greater than the capacity, so we've got to evict the 2 and put in the 3. So now if you look at the LRU cache, it has the 1, 1 and the 3, 3. So now we're going to try and get the 2, which should return -1 because, yeah, we don't have a 2 in there. So now we're going to put 4, 4 in. So 4, 4 looks for the eldest entry, which is still the 1, because although we got the 1, we put in the 3 afterwards, and so the 1 becomes the least, what is it? Yeah, the eldest entry. And so we have to evict the 1 because the size is greater than the capacity. So now if you look at LRU cache, it's 3, 3 and 4, 4. Now we're going to get, or look for the negative, we look for the 1, which is going to return -1 because we don't have a 1 in there anymore, the key 1. So now we're going to pass in key 3, which return the value 3. Result is 3. And finally, we're going to pass in, or we're going to try and get value 4. So we pass in the key 4, returns value 4. And that is pretty much it. So let's run this through LeetCode and see what happens. It's accepted. This is example 1. And we submit it. It is faster than 70, basically 71% of the entries, and it uses least amount of memory in almost all the submissions. So that's good news. All right, so finally we'll go through the time and space complexity. So time complexity in this case is O of 1. We're just putting, getting, removing eldest entry. There's nothing that's going to increase the time on that. But the space complexity is O of n. So as you can increase the capacity, then the cache gets bigger. And so the big O notation is O of n. And that is it. So hopefully this made sense. Let me know if you have questions, and I'll see you next time.